This is a big and diverse group of students as far as I understand it. So before I enter this, I mean, I prepared it for a very mixed audience, but I like to just get an impression of how many biologists are in the audience. Can you raise your hand? Okay, there are a few. How many chemists? One. Physics. Astrophysics. Okay, majority. I'm an astrophysicist or astrochemist, but I try to keep it at a level that maybe some astrophysicists may be bored in the beginning, but at least we make sure we get all the others along somehow. So my task is to talk about the physical and chemical properties of these planet-forming disks. I don't call them protoplanetary disks anymore because I think we've seen some evidence that the objects we are studying are actually showing some level of planet formation inside. So the point is, it was very hard to make a choice to keep this in 1 hour or a little bit more than 1 hour. So I first want to go through some basic facts to get everybody on the same page about what these disks are. Then I want to talk about observations of gas and dust in disks, because astronomical observations are not very easy to understand for everybody, and especially with these disks that contain a lot of dust and gas. We're using so many different observational techniques to understand what is inside them and how they evolve that I need to explain that a bit. Then I want to use those disk observations to show a little bit overall how are these disks evolving and what do we know about that. And then I have to give you a tiny little preview because the next lecture will be given by Nada on planet formation. But since we are witnessing some of those planet formation processes in these disks, I will just give you a tiny sneak preview of what is happening. And then I want to highlight very selected results about dust being a tracer of planet formation in these disks, and some recent observations that tell us about these processes. And then use the gas as a tracer of planet composition, and again, it's very selected observations because 1 hour is way too short to deal with everything. And at the end, I want to give you the solar system context. So how do we actually fit in all of this? Because we are observing here usually several tens to even hundreds of these protoplanetary disks, and not everyone is around a solar type star, and not every disk will evolve into something that looks like our own solar system. So since I had to select a lot of things, I want to draw your attention, if you want to learn more about protoplanetary disks in general, theory, modeling, meet observations. We had a summer school on Ameland that Manuel Güdel was actually also part of, where we just dealt with everything concerning disks, how they form, how they evolve with time, and everything we know about them. So all of this is open access, so if you want to go there, you find equations, like somebody asked for. You don't see equations in my talk. If you have questions, just ask them in between. I don't mind. So circumstellar disks, some basic facts to start with. These disks form in star-forming regions. Every young star is basically surrounded by a disk. That is what we learned from the Hubble Space Telescope when it looked, for example, at the Orion Nebula. There are a lot of young stars in the Orion Nebula, and many of them are surrounded by nebulosities. And each of these nebulosity you can basically think of as a planetary system that is forming. This particular star-forming region is about 400 parsec away, 1,300 light years. So actually, when we are observing it, we see the light that was emitted from there at 1,300 years ago. So we are looking in the past, even though not the same way as cosmologies. The youngest stars, they are actually less than 1 million years old. So they are really very young, and they don't have mature planetary systems. They still contain a lot of the primordial material that goes into planet formation. And now, how do we think these disks look like? This is a sketch that just shows you that these disks are actually structures that surround the central star. We know they are rotating. We know they contain a lot of gas, which is the yellow stuff you see here, and they contain a lot of these small dust grains. And they're really tiny little dust grains, smaller than even a micrometer in size, so smaller than what your hair is. Now, the grain sizes can be up to millimeter in size. This is what we see from observations. This is purely because this is the only size of dust, or this is the largest size of dust grains that we can receive radiation of. If there were kilometer-sized planetesimals, big rocky things in these disks, we would not receive any radiation from them that we could detect. So in a sense, when I'm talking in the next slides for the rest of the talk about the solid component in these disks, or the dust, what I mean is the stuff contained in up to millimeter-sized grains, because no observations tell us, unless indirectly, that there are already larger bodies in here. The grain material is very similar to what we know on Earth, so it contains silicates, it contains carbonaceous stuff, polycyclic aromatic hydrocarbons, so quite poisonous stuff as well. And we know that there are ice mantles around these grains. So if we are actually in the cold outer parts of these disks, we see, for example, water ice. The disk masses, which is also interesting to note, is up to a few percent of the stellar mass. And coming back to the question that was just asked about whether there is evidence for these disks helping, breaking, for example, of the rotation of stars, and whether there's coupling of magnetic fields, and this plays a role. This relation, that it's up to a few percent of stellar mass, holds all the way from the M dwarfs to A-type stars. So across the whole mass range of stellar masses, this relation holds, meaning if there was, if we see less breaking in the M dwarfs, why would this be the case? I mean, if this is a constant relation, then the disk should help respectively the central star in the same way, no matter whether it's an M dwarf or an A-type star. So even without understanding magnetic fields, this would be my simple answer, that maybe the disks do not play a huge role. And the gas to dust mass ratio in these disks is 100. This is interesting to note, because we need these dust grains to build a planet like Earth. But actually there's 100 times more mass in the gas, and only planets like Jupiter and Saturn, for example, they benefit from all this gas in the disk. But to build terrestrial planets, in principle, you only look at like 1% of the mass of the disk. Now the typical sizes are 0.01 to a few hundred astronomical units, 1 astronomical unit being the distance between the Sun and the Earth. And if you want this in kilometers, you see it goes from millions of kilometers to 10,000s of millions of kilometers. These systems are huge. Our own solar system, if we just count in the planets and even include Pluto for historical reasons and because we like him, it's about 50 AU in size. The interesting thing is the scale height. So the scale height is basically the pressure scale height of the gas. And interestingly enough, the height over the radius is only a few percent. So you see that this sketch is actually giving you a wrong impression. It's kind of misleading, because these disks are very, very thin structures. So they are geometrically very thin. It's just that it makes no sense for me to show any plots if I put them on scale. So we generally put them on a different scale for height and radius, so that you can see what happens inside. Another thing is, even though these disks are geometrically very thin, they are not super flat structures. They're actually opening up. And this is a very important result from early observations already more than 20 years ago, because somehow we needed to get this outer disk warmer than it would be if it was a completely flat structure. And the point is, if we have a flaring surface, the radiation from the star can actually interact with the surface even at larger distances. And about half the radiation gets scattered into the disk, and half of it gets scattered away. So there's actually more energy being put into such a flaring disk structure than if it was completely flat. And we needed that to explain the temperatures. And just to give you the perspective about the conditions inside, because this is important when you talk about, for example, chemistry later on, the typical particle densities in the inner disk are 10 to the 15 particles per cubic centimeter. So, and the temperatures of a few thousand Kelvin. So if we turn that into pressure, we are at around 10 Pascal. If you go into the outer disk, which is much more tenuous because we have a very strong gradient in radial direction, but also in vertical direction of density, we find here densities that are more similar to what we find in molecular clouds. Very, very dilute gas, even better than the best vacuum we can make on Earth. And the temperatures are extremely low, maybe a few 10 Kelvin. And as you see, the pressure there is extremely low. So you can already imagine that processes that happen here will not happen here and vice versa. These disks provide us with a unique laboratory that spans orders of magnitude in pressure, temperature, density conditions. So lots of different processes will happen, which also made it very difficult for me to select what to actually talk about. But just to give you an impression about what happens in these disks, there's a lot of interaction between the radiation of the central star and the disk. And this is kind of what shapes the disk structure. I already alluded to the fact that these disks are flaring structures. And this is partly also because the central star is putting out a lot of X-rays, UV, etc., that is heating the gas even at larger distances. And so actually these structures puff up, as we say, as we go away from the central star. And so both X-rays and also UV can actually enter the disk either by direct absorption or it gets scattered by dust grains. And the same is true for the X-rays, although the scattering happens also by the gas. And then at the same time, we have other radiation sources as well. They are cosmic rays, even though they are particles, but they put in energy into the disk, and usually we consider the cosmic rays to just come from all directions. But since most of our models are only two-dimensional, I just put the radiation source like this, so they can penetrate the disk in many places up to the midplane easily. And the midplane is actually where the planets are forming. And then we also have stellar particles. Those are very energetic particles sent out by the sun, for example. We heard about that in Teresa's talk just before. And those can penetrate radially into the disk up to a certain depth as well. So that actually drives a lot of the temperature. This actually sets the temperature in the disk, but it drives also a lot of chemical processes that happen in disks. And the other processes that shape the structure, the overall structure of disks, is actually dynamical processes, and I indicate here dust, gas, and also planets. For example, what happens to the dust grains, and we come back to that, dust grains can actually radially drift inwards if they're large enough to not being well coupled to the gas flow. They will also vertically settle to the midplane, collide with each other, and slowly grow in size. The gas itself, if we think about the star formation process, and this is something that Bruce will cover tomorrow morning, the mass is actually flowing in from a kind of large molecular cloud when the star is formed, but it's flowing in and the mass is accreting through the disk onto the young forming star. And so there is generally a kind of steady gas flow through the disk that is building up the central star. Even though we still do not understand how this happens, how the angular momentum is lost, etc., there's still a lot of open questions. There may be winds, for example, especially here at the inner radius of the disk, in the interior parts. Winds, they can originate from radiation or from magnetic fields. We are not entirely sure about it. And then the gas can be turbulent. We don't know yet. There are probably very low levels of turbulence, but if we do have some turbulence, then there will be some stirring up of material and some kind of mixing constantly happen in these disks. And then we have the beautiful planets that we all like and love and want to make in these disks, and they will have a profound impact as well on the disk if they are massive. If they are, like I show here, like a Jupiter, they will have a strong interaction with the disk itself. They can open gaps, they can prevent actually dust flows going across their formation site. And so there are lots of processes that happen and that shape these disks. So how do we actually come to know this? In order to know all of this, we need to observe these disks, and then we apply all the physics we know, all the chemistry we know, in order to see whether we understand the observations. So what can we actually observe? What you see here again is a sketch of these disks, and you see here a diagram which we call the spectral energy distribution, because we put the energy here in units of nu times the flux at a particular frequency, and here versus the wavelengths, which is inconsistent, but astronomy is all over inconsistencies. So this is the energy versus the wavelength. And what you see here is a typical stellar radiation field. So you see it peaks more or less in the optical part, and then it declines strongly towards the infrared wavelengths, and at radio wavelengths, these stars are putting out very, very little energy. But then what has been seen with the earliest infrared observatories that were launched into space was that there was actually an excess of radiation at infrared wavelengths was much stronger than what we expect from the star itself. And this excess radiation is coming from the disk. It is the thermal radiation that comes from the small, tiny dust grains in the disk. And it's thermal radiation. So the amount of radiation depends on how warm the material is, but also on what the emitting surface area is. And this is the reason why, if there was 1 kilometer size rocky body in that disk, you wouldn't see it, because its surface area is small compared to taking that kilometer-sized rocky body, putting it into tiny micron-sized dust grains and spreading it out all over the place. And so it's a surface area issue why we can't detect kilometer-sized rocky bodies. But we detect micron-sized, millimeter-sized dust grains. And this is typically the spectrum we see from a disk. And it comes from different regions. So the near-infrared radiation comes from the inner disk, because this is where the dust grains are very warm, usually around 1,000 Kelvin. And as we go further and further out, the radiation shifts to longer and longer wavelengths, because the dust material becomes colder and colder. It is a stellar radiation field mainly that is heating that dust. And because the radiation field is diluted as 1 over r squared, there's less and less energy put into the dust grains in the outer disk. And you see this here from a nice simulation. It shows two interesting things. So the colored boxes here show where roughly 50% of the dust emission is coming from if I take a crosscut of such a disk. So this is the height in the disk, this is the midplane at 0, and this is the distance from the central star. And we see here in this magenta, this is a scattered light emission at 1 micrometer. So it's light that is scattered by small dust grains. The radiation comes from the central star, which is somewhere here. It hits the surface layer of tiny dust grains, and like I said, about 50% gets scattered away, and this is what we actually see here. So we see the large surface actually shining in scattered light, and we come back to that when we look at scattered light observations of disks. At the same time, when we look at longer wavelengths, to put it to the extreme, this is like 1,000 micrometers, so this is wavelengths of radio telescopes. What we see is predominantly emission from millimeter-sized grains, from the very cold grains here in the outer disk. And interestingly, what you see also is the emission is really coming from very close to the midplane. So even though at short wavelength, the optical depth to which we can look into the disk is not deep. I mean, we only see the surface. At radio wavelengths, we generally see all the way through the disk. The material becomes optically thin at radio wavelengths. And so at long wavelengths, we probe the cold millimeter-sized dust grains in the outer disk. This is interesting because actually, as I said, the planets are forming in the midplane. And so currently, going to very long wavelengths is our best way of actually observationally reaching that midplane region where the planets are supposed to form. Now, the gas is a bit more complex, and the reason for that is dust grains, since they are large solid bodies, they radiate at all wavelengths. They are a continuous radiator, as we say. The gas is more complex. Not only do we not have a single gas, I mean, it's not like it's all hydrogen. We do have carbon, oxygen, and other elements in there as well, and so they go just off and they form molecules like carbon monoxide, water, HCN, and all of that. So we need to take that into account. And on top of that, a gas is not a continuous radiator. All these molecules have their discrete energy levels, and so they will radiate at very specific wavelengths. For example, we can look at the CO molecule. This is what we call the low rotational lines that we see in the submillimeter. This is a CO molecule just rotating happily at temperatures of, say, 5 to 50 Kelvin. Just very slow rotations, and we can observe them with radio telescopes. And what we see is the CO gas that is sitting here in the outer disk, very cold. But the same CO molecule, if we put it in a very hot environment, like 1,000 Kelvin, it will not only rotate, it also starts to vibrate. So the bend length will actually start to change. And so what we then see is the rho vibrational transitions in that CO molecule, and they occur at much shorter wavelengths. So the CO molecule sitting here in the inner disk where terrestrial planets are forming is sitting there at temperatures of, say, 1000 Kelvin, and it will emit in rho vibrational lines in discrete bands around 2 to 5 micron. And so we see that even for one molecule, we will have a very different set of signatures that we see from these disks, and we can observe them either in the near infrared or all the way to the radio. And the same holds also for molecules like water that have a very rich spectrum. And there are lots of other tracers we can use. And so in that sense, gas observations are a little bit more tricky than dust observations. The good news is if you have full access to the whole wavelength range, you can actually start to just scan the disk surface. Just go all the way from the near infrared to the radio, and you will build a complete picture of how these disks look like in the gas. Gas observations are also more powerful to some extent than dust observations, because not only that each molecule, so you have access to multiple molecules, each molecule and wavelength probes a different disk region, but also the gas can provide kinematic information, which the dust cannot. And this is through the Doppler effect. Because, as I said, these disks are actually rotating structures. So you see here the face-on view of such a disk. And this is the velocity field that we see. And you see actually, if we look as an observer from here, this is the velocity field from a top-down view. So we see at zero velocity, the disk is emitting only in this particular narrow part, while the maximum velocities, or the peak of the line profile, is actually given by those closed velocities. So these are isovelocity contours, by those velocity contours here. This is the line profile we see. So with the Doppler effect, if we suppose for a moment this is a CO molecule, what we see is actually that one side of the disk is rotating towards us, and so the line becomes blue shifted, and one side is rotating away from us, and so the line becomes red shifted. And the amount of radiation we actually receive from these different velocity bins of the disk depends on how much surface area is available in that particular velocity bin, and this is what is color-coded here. And so the last actually closed dipole contour that you see here is the one giving rise to the maximum redshift emission that we see. So this is an interesting thing, because we can actually use it to demonstrate how fast these disks are rotating. We can even use it to measure the central mass of the star, because you can, if you know how fast the gas is rotating at which distance from the star, you can use Kepler's law to infer the central mass. And what you see here is what we call a moment map that actually beautifully illustrates that these disks are rotating. So this is the velocity if we integrate over the entire line profile. So you see this is redshifted, this side of the disk, this is blue shifted. So we know exactly which way the disk is rotating. We even know exactly where the rotation axis is situated, just purely from the observations, purely because we measure that velocity shift in the line profile. And the interesting thing, and that's why I included a movie, is that now with the big radio telescope that we have at our disposal, and this is, for example, ALMA, we actually do get the full spatial resolution and the velocity resolution as well. So what we actually get is what we call channel maps. And so what you see here is how the emission, so we step here through that velocity range, all the way from blue shifted to red shifted, and we see which parts of the disk are actually lightening up as we step through. This is the CO molecule emitting. And as we go from the one side of the disk, basically rotating very extremely towards us, to the other side rotating extremely away from us, we step also through the zero part where the disk is very linear. So this is zero, and then it goes to the other side. So this is extremely powerful, because now we can measure not only the velocity shift, but also we see at which location the gas is emitting at that velocity shift. So before we go into any of the observations, I would like to know if there are any questions about these basic facts. because this is a lot. Yes?
Can I just ask about the dust that was there? Is the pre-solar dust, or you imagine already that all the pre-solar dust was destroyed, everything is re-homogenized, and then it is solar system dust?
No,
or we don't know?
No, we know definitely for our own solar system from the records that there are pre-solar grains. So a certain fraction of dust has to survive. Apart from that, I think there are two schools of thought. There is a solar system community who likes to think that everything vaporized at some point and recondensed into solids. And there's the astrophysical community that likes to think that all the dust is inherited from the molecular cloud when the star plus disk is formed. So the molecular cloud also contains gas and small dust grains. And that material is used to build up the disk. And only what happens then is that that material is steadily growing in size. But the seed is the original material. So those are the two schools of thought, I would say.
Is it gas ionized or is it nuclear atoms?
In the surface of the disk, the gas is ionized. In the midplane of the disk, there's usually a very low level of ionization, which is only driven by cosmic rays.
We used Doppler shifting to get the velocity, but isn't that just radial velocity? So how do we know the exact? So we should just look at those disks, which you can see like this shape.
No, sure, you're entirely right. There's a projection effect.
Yes.
So one of the things we see, so when you look at the dust continuum, you can see how elliptical, for example, a disk appears. If it appears very round, you know you're looking at it face on. If it's like tiny like a smudge, it's edge on. Anything in between, you can basically deproject. So you have some idea about what the inclination of the disk is. And the same is actually true for these channel maps as well. So they give you the inclination. And so you do have to do the deprojection. You're right. The Doppler effect, we only see the line of sight component of the velocity. So for some observational experiments, you want to use edge-on disks. For others, face-on disks. And there's some experiments you want to have in between. So you have to fine-tune your life. Yeah.
So how does the gas to mass ratio changes with age and this other type?
I'm not going into that discussion because that's, I think, even at the moment, a huge open debate. And there are different viewpoints on that. So we know that, and I would show that both dust and gas are evolving with time. But whether they are evolving at the same pace, or if the evolution even happens in the same way all the way at different distances from the star, I think we still need to figure out. I think there's evidence it's evolving faster in the inner disk than in the outer disk. But about whether gas and dust are doing this at the same time in the same way is still highly debated. So let's apply what we just learned on disk observations to see how the disks are evolving overall. So the dust evolution is something that has been probed, at least for large statistical numbers of disks, using infrared satellites, such as, for example, the Spitzer Space Telescope, which did a huge survey of many regions in which young stars are forming. And all those regions you see basically color-coded here. All of these regions have different ages because they contain usually tens or even hundreds of young stars. We can age date them very precisely, relatively precisely, I should say. And what you can then look at is the frequency of young stellar objects that actually do show an infrared excess. So I repeated that plot that I showed earlier to remind us we are now looking at this part of the spectral energy distribution. This is where Spitzer operated, and this is where these surveys have been done, at about 6 micrometer. And if you remember what I said, this is very warm dust that we are tracing in the near infrared, so it corresponds to the inner disk. And if we now look at the frequency of disks where we do detect an excess here above the photosphere, we see that excess in the beginning is very high, towards 100%. And then as the star-forming regions become older, so this is age in millions years, this is 5 million years, the frequency of excess actually drops. So what it means is that we lose that emission from the inner disk. So something is happening in the inner few, maybe up to 10 astronomical units of these disks over a time scale of a few million years. As I also told you, in the long wavelength range, I mean, we are, with these observations, not sensitive to what is happening here. So in a sense, it only tells us that the inner disks are disappearing on these timescales. Now, there have been lots of studies of these spectral energy distributions, and I want to mention one interesting aspect here. This is again the same plot of spectral energy versus wavelengths, and you see here in color, for example, what we call pre-transitional disks. So you can go and classify all those spectral energy distributions, and in this particular case, we do it with respect to the median in a very well-known star-forming region, namely Taurus, which has an age of about 1 to 3 million years. And you see that the blue spectral energy distribution here is distinctly different from what we expect from the median distribution at that young age. And there must be a reason for that. And the same here, this is what people call a transitional disk. You see that the green curve here from those transitional disks lies very well below that median spectral energy distribution. And the interesting thing is that you can attribute that lack of emission now to a lack of material in the inner disk. So this is exactly what I showed in the previous plot. So some disks start to lose that inner material, and so they develop a lack of infrared excess at short wavelengths. You see that this disk at 5 micron has radiation very similar to what you expect from the photosphere. So it would be classified as a disk that has lost its inner material. And I draw the sketch here. Actually, I took it from a nice review by Catherine Espayat. So you see that around the central star, there's a huge kind of hole that developed where there's very, very little material left, and then the disk is starting. While in this particular case, there's still some little material left that is giving rise to radiation here at short wavelengths of a few micron. And people think they can represent that with having a tiny little inner disk that is still left and containing some hot dust. And then there's a large outer disk once the spectral energy distribution comes up to the same level as the median in Taurus. So these are different geometries that show us a little bit what the diversity is that disks can undergo in their process of making planets, in their process of clearing that inner disk. Now, in general, there's not one only possible explanation for this. Of course, we all like to think immediately about planet formation. So there are planets forming here, and they actually use that material to form. They clean out the gas and the dust in the inner disk. But there are other alternative suggestions as well. So disk evaporation can do something similar. It will also clean out the inner disk first, and it would be consistent with having a transitional disk geometry like this one. And then also we can simply apply the equations of grain growth and removal, so dust grains as they grow large and as they decouple from the gas because they do not have enough interactions anymore with the gas, they can actually very rapidly migrate inward. And so we can also explain such cavities with a combined process of grain growth and radial migration. And so I just want to draw your attention to the fact that there's not still a unique, commonly accepted explanation for what these different disk geometries mean. Now, as I said, this is a near-infrared, so it's the inner disk. The outer disk we can also study. Now we turn to radio telescopes. And of course, there's a long history that I happily omit here, even before ALMA. But I show here one of the most recent figures that came out of a combination of several surveys that ALMA did in young star-forming regions. And we see here the names of those star-forming regions. Taurus is what I just introduced to you, 1 to 2 million years. Some people say 1 to 3. And then we go all the way to older and older star-forming regions, up to Upper Sco, which is another star-forming region, at an age of about 10 million years. So there's definitely a trend with age. And this is a plot from a nice paper by Marion Villeneuve that is about to be submitted. And what you see is the cumulative fraction of dust over stellar mass as a function of the mass of the dust over the mass of the central star. So what we measure with the radio telescopes is actually how much dust mass, how much millimeter-sized dust mass do we have in these disks. As I told you initially, the initial disk mass that we measure always scales with the central stellar mass. So if a star is more massive, if we have a 2 solar mass star, it also has a disk that is more massive. So by plotting it this way, we actually correct for the fact that in a star-forming region, you will have some low-mass stars forming and some high-mass stars forming. So we take out that dependency because naturally they have different amounts of dust around them. And so what we see here is then that the different star-forming regions show different cumulative diagrams. And in the end, even though it seems like it's a super nice evolution with time, you're very tempted to say immediately, oh, well, yeah, I see the outer disk is also evolving on timescales of 5 million years. We have to be aware of the statistics. So if we use a proper statistical test to check whether these, say the first 3, can be drawn from the same distribution, the test tells us that the first 3 can still be drawn from the same distribution. So they are not significantly different from each other. But the last one, so upper score at about 11 million years, is definitely different statistically. And so what we can say is that it seems that the outer disk is also evolving on timescales of several million years. And it seems like, but this is only a hint, initially the evolution is not very fast, but then suddenly if you jump across a certain age line, in this particular case, if you go beyond 5 million years, things seem to start evolving. But we definitely need more surveys in order to characterize this better. Another interesting aspect is not only how the total amount of material you have for planet formation is evolving with time, but also how is it changing in its composition. And I had to be, again, very selective because there's lots of beautiful work done on that. But just to show you a very nice example, even though it's already quite old, but we are still waiting for the new instruments to come up in order to repeat those measurements and enhance our sample. This is a sketch of a protoplanetary disk again. And these people, so this is Roy von Buckel in 2004, they used an interferometer, which is too complicated to explain here in detail, but some people may know what I'm talking about. You can use an interferometer to pretend that you have a telescope with an incredibly large spatial resolution. And so they could get a spectrum of that inner disk, only the inner 1 to 2 astronomical units, and compare it to a spectrum they could get from the region outside up to 20 astronomical units. And what they focus on is the silicate feature. So in principle, on that smooth spectral energy distribution that I showed you before, I cheated when I said that the dust only emits continuum radiation. There are solid state features that the dust is emitting. In this particular case, if we're talking about silicates, it's bending and stretching modes of SiO. And so this is a particular strong feature at around 10 micron. And as long as the grains are only up to a micron or a few micron in size, they will strongly emit in that particular vibrational band. And so they focus here on the 10 micron band because it contains very interesting imprint of what the structure of that silicate dust is. We know we can have, even on Earth, amorphous silicate dust, but we can also have crystalline silicate dust, the crystalline being extremely ordered. So if the dust is extremely ordered, it actually shows a lot of peaks in that particular feature, while if we are dealing with amorphous dust, it's generally a very broad, peaky feature, and for the crystalline dust, it's not as centrally peaked and it shows a lot of substructure. And so what they showed is actually that the silicates they see in this sample of disks is very crystalline in the inner disk, and it's still amorphous in most parts in the outer disk. And so that's a very interesting aspect, telling us that somehow dust is processed from amorphous. I mean, in the interstellar medium, when you form dust grains in the first place, most of them will probably be amorphous because there's some kind of coagulation process going on that is not extremely ordered. And so there is some processing, and that could be, for example, annealing of the dust or something like that, that actually turns it from amorphous into crystalline in the inner disk. And we just heard in the talk before, there are lots of possibilities for doing that because we have X-ray flares, we have flares in the EUV, there may be even shocks in the inner disk that can provide the heating so that we can anneal the dust. So there is a lot of processing of that solid component going on in these planet-forming disks. And people noted a strong similarity between the inner disk and actually what we see in cometary dust in terms of the silicate crystallinity. Now, this is not only true for dust, we can also look at ices. So we know that in the outer disk, when the disk becomes extremely cold, water vapor, for example, will freeze out and can form ice mantles around these grains. And we can study the thermal emission of those ice mantles as well. And this is a very unique study so far that has been done by Michiel Min, using a combination of data from the ISO satellite that flew like more than 20 years ago, almost 30 years ago, I would say, and the Herschel satellite that flew more recently. And what we see here is, again, this is part of the spectral energy distribution, but only shown as flux, not nu, F nu, versus wavelengths, but only in the mid to far infrared, so between 30 and 100 micron. This is exactly where water ice has its strongest thermal emission features at 45 micron and also around 60 micron. So what you see here in blue is actually, this is the opacity of ice. So you see these strong features in those two locations. And interestingly enough, just like for the 10 micron silicate dust feature that I explained here, also for the ice feature, there is a very distinctive change in that feature depending on whether the ice is amorphous or whether it's crystalline. And you see that the crystalline ice is very peaky. So this is the blue curve here, it's crystalline ice. The amorphous ones, which are more like the green and the pink ones, they are more flat and not as peaked as the crystalline ice. And now what they did in their work is actually compared the shape of these features that they find in this particular planet-forming disk. And they found that they have a very high fraction of crystalline dust in the outer disk. We know because we can model these disks, and we also know from other wavelength observations what the shape of the disk is roughly. So we know that this emission feature is coming from well beyond 10 astronomical units. So it's coming from very far out. So the water ice should be extremely cold, and still we see it's crystalline. So at some point it must have been above, say, 100 Kelvin or so, which is the temperature limit, or 120 Kelvin, which is the temperature limit to make ice crystalline. If you form it under very, very cold conditions in the outer disk, or even in a molecular cloud, it will be formed at temperatures of 20 or maybe 50 Kelvin. It will be amorphous. So it's somehow you have to bring it up at high temperatures in order to turn its crystal, in order to make it crystallize, to have a crystal structure. And so apparently that water ice that we observed from this object has somehow been altered in its composition. And then there are more interesting things we see now about dust evolution. And I'm coming back to the beautiful era of ALMA data. So what you see here is a very nice compilation of 6 different images of protoplanetary disks. They almost look like as if an artist has made a sketch, but these are actually images that come from the telescope. And what you see is a whole series of objects, maybe the most famous one being HL Tau here, that have been observed with ALMA at very high spatial resolution. Scales of a few astronomical units have been resolved. And what we see is a lot of substructure in these disks. Now, we can ask ourselves what may be at the bottom of this substructure, especially there's one, the very first object that was observed by the ALMA partnership during the commissioning of this extremely long baseline mode of observations. This is an extremely young disk, less than 1 million years old, and still we see all this substructure. So of course that calls all kind of theoretical modelers onto stage, and everybody tries to apply their own ideas about what causes this substructure, especially the nice concentric rings. And giant planets that are forming inside these disks is only one possibility of explaining the structure. Alternatives can also work. and have been suggested, such as, for example, you can have binaries at the outside that actually shape the disk and produce spiral arms like this one. You can have gas instabilities that also lead to the production of concentric rings, or even something I forgot to mention here, if you have ice lines in these disks, if your gas is slowly freezing out in the form of ice, it will happen at different distances. For example, water ice has a higher condensation temperature than carbon monoxide ice. And so you will have distinctive radial zones in the disk where you have either only water ice or you have a combination of water and CO ice and CO2 ice. And so that may also give rise to the formation of such structures. So the jury is still out. We don't know yet. There's lots of ongoing work here. And last but not least, the gas evolution. I focus mostly on the dust evolution because historically it has been much more studied, because we didn't have for a long time the sensitivity to do these studies for the gas in exactly the same way for statistically relevant samples. But now we are starting to get there. So this is a plot that shows something very similar to what I showed initially for the dust. So this is the fraction of stars that are actually accreting in a star-forming region as a function of age. And what you see here in red and green are actually collections from H-alpha data. So if a star is accreting mass from the disk, we think it happens somehow, maybe through what we call funnel flows, or somehow the material has to accrete from the disk onto the star, and this may happen through a very complex geometry, but in any case, it will be somehow hot stuff falling onto the central star, giving rise to emission in H-alpha. So if we study that kind of H-alpha emission and the strength thereof as a function of different star-forming regions, we can see that that fraction is also declining as a function of age, actually on very similar timescales as we saw for the near-infrared, meaning for the inner dust disk. What we overplot here in blue is actually the results from a large survey that we did with the Herschel satellite. And here it comes the caveat: because of the sensitivity issues, these gas surveys are often not unbiased surveys. If I just do dust observations, they are fast. I don't need the same size of telescope. I don't need the same sensitivity to get to hundreds of these objects. So I can do unbiased surveys of entire star-forming regions. For the gas, because I need a much higher sensitivity, I actually do have to make a pre-selection most of the time, or I turn to samples that have been pre-selected by somebody else anyway with certain biases. And so all these gas studies generally come with certain biases. But even for the gas observations from our survey, which focus on one specific cooling line from the gas, one specific emission line at 63 micron, and it took hundreds of hours of observing time, we looked at star-forming regions like Taurus, Chameleon, and Eta Char, and we see a steady decline. So confirming somehow also what we see with the H-alpha measurements. The interesting thing here, again, is H-alpha, as I said, it's probing the emission of hot gas that is accreting onto the central star. So we are talking about something that happens in the inner disk. The 63 micron emission of oxygen, if you remember, and you may not, but you can go through the slides, that initial plot I had about where the different emission of gas lines is coming from, the 63 micron emission is coming from 50 to 100 astronomical units. So what we are tracing here is the evolution of gas in the outer disk, with the caveat that it's not unbiased. This is actually the best that has been done so far. It's a re-reduction of all young stellar objects that live in the Herschel archive that the mission has ever observed during its lifetime before it ran out of cryogen. And it's divided into different ages if you want. You can take these classes as representative of ages, and Bruce will talk more about that tomorrow morning. So sorry for not having that talk before mine. But class 0 is usually much, much younger than 1 million years. Class 1 can be maybe up to 1 million years, and then class 2 is like 1 to 3 million years if you want, just to have some ballpark numbers. And what you see here is the luminosity of that oxygen 163 micron line. And you see a clear evolution in how much radiation we get from that line between the very young sample, which is this magenta one, then the class 1, which is the red one, and then the class 2, which is the blue one. And these dashed lines are the sensitivity limits. So you see we are still only probing the tip of the iceberg. The Herschel satellite was not sensitive enough, and that's also why we have no unbiased surveys. We definitely pick up always the brightest targets anyway. So it's a tough life. Now, the question is, can we actually catch planet formation in the act? What is the role of dust in planet formation? And this is where the very tiny little interlude comes in about planet formation and how dust fits in there. We have to go from those tiny, tiny little dust grains that we observe in space and that we see in these planet-forming disks, all the way to making a planet like Earth. And this is 12 orders of magnitude in radius, 36 orders of magnitude in mass. This is not an easy task. I'm going to skip all the details because Nada will talk about them in his lecture. What you need to remember is small dust grains couple very efficiently to the gas just because you have lots of collisions between those small dust grains and the gas, and actually the small dust grains are also not very massive. The large dust grains decouple from the gas, and so what they experience is what we call a headwind, because they constantly bump into the gas that is going at a different speed as they are going. And the gas pressure maxima can actually capture dust grains. So all of this actually leads to certain features that we can see in our dust observations just because of that interaction between gas and dust. We see that dust grains can drift radially, and the timescale depends on their size, but also on the underlying gas structure. So what is the gas density as a function of distance from the star, what is the temperature, etc. The dust grains also settle towards the midplane. This is a process that happens also over time, and it happens differently in the inner disk and in the outer disk because, again, it depends on the gas density. And as I showed you initially, the gas density is extremely high in the inner disk and extremely low in the outer disk. And this will also depend on how much turbulence there is, because you can imagine the process that counteracts that gravitational settling of the dust grain through the gas will depend on how efficiently it's actually mixed up again. And then dust grains collide with more or less success to grow. So we constantly also see a population of small dust grains that comes probably from destructive collisions. So the next lecture will actually provide much more about that. But let's go back to the observations and see if we have any hint of these kind of processes going on in the observations of planet-forming disks. And there's a very nice example here from work by De Gregorio Monsalvo from 2013. These are ALMA observations, and what you see here is the dust, and in the blue magenta line is the gas. And what is plotted is actually the surface brightness that we see both in the continuum here and also in the CO line here as a function of distance from the central star. What you immediately see is that those two profiles do not look the same. So the surface brightness suggests that the dust is actually stretching out not as wide, as far away from the star as the gas is doing. And this is very interesting because this can be explained by what I just told you, radial migration of dust. So if we turn to computer models, we can actually put in all the physical equations that we know and all the laboratory experiments people did on dust grain collisions, etc., in order to understand their behavior. We can see how a model would behave if we include grain growth, drift, and also fragmentation of dust grains. And what you see here is how the surface density changes as a function of age. So different colors are different ages. And actually this line here is the gas, and this line is the dust. So you see that after a certain time, indeed, there's a mismatch between the gas surface density in the disk and the dust surface density in the disk. So they show different, say, radial extent. And this is a very natural consequence, at least it's one possible explanation, that we do have dust growth and radial migration. And we could claim that we have actually seen that now in our observations. The other interesting aspect was that the dust grains can actually vertically settle towards the midplane, so they will slowly sink down because of gravity, and on their way they can actually start to collide with each other and to grow to larger and larger dust grains. And the question is that seen? Well, let's turn back to this beautiful ulnar image of HL tau. If you remember, maybe even already from the press release, these rings were not only very concentric rings, but they are also not showing any big difference in their width between the minor and the major axis of the disk. Now, if the disk had a very profound height, because of the projection effect, we are not seeing that disk face on, no, we are seeing it inclined. Because of the projection effect, you would expect to see the rings to be much wider in one direction than in the other. This is not the case. So if you apply detailed models to it, you can actually use them to derive how flat that millimeter-sized dust is. And this is what Christophe Kamp did in his models, and he found that, say, the scale height of millimeter-sized dust grains, although dust is not a fluid and has not a scale height, but somehow we have to measure it, at 100 AU is about maybe 1 to 2 astronomical units. So you see, if I go out 100 astronomical units, my dust grains are confined to about 1 astronomical unit. That's how thin that distribution is. It's not a thick disk. It's a geometrically very rather thin disk. And of course, you can immediately use that to learn about turbulence in these disks, because if the turbulent levels were extremely high, the millimeter-sized grains would be steered up by the gas turbulence. The fact that they are so thin puts a constraint on the turbulence in the disk as well. So very low turbulence is required. And just to remind us, the explanation for the rings is not necessarily only planets, it can be something else as well. There's more substructure seen, for example, from scattered light images. If you remember what I told you initially about observations, in the radio we actually look at the millimeter grains close to the midplane. If we look at scattered light radiation at short wavelengths, we see the surface of the disk. So this is a very nice example of those scattered light observations, and what you immediately see is this is not simply the projected effect of seeing an inner ring somehow. I mean, there are 2 gaps, if you want, in here, which are hard to explain. I mean, if it was just an inclined inner disk that we would see, it should be at least closed as an image, which it's not. And so interestingly, people actually infer from it that there is a tiny little inner disk that is blocking the light from the central star and casting shadows at these positions at the outer disk. So we can learn a lot about the intriguing geometry of these inner disks from scattered light observations. So there's a huge potential here. And in the view of time, I'm going to skip the questions for a moment and get to my last point, namely the gas as a tracer of the composition in these disks. Of course, gas can also be used as a tracer of the physical structure of disks, but I'm not going into that, because the unique aspect of gas is that it can also probe the chemical composition. And what you see here is a sketch of how such a disk looks like in its chemical content. And this comes back to a question earlier on the ionization. Because the radiation from the central star hits the surface directly, actually the surface of these disks will be very atomic and ionized. Then as we go deeper into the disk and more of that direct stellar radiation gets blocked by dust grains, for example, we reach a layer where molecules start to form, but there's still substantial ionization, so we form a lot of ion molecules, like for example HCO+, N2H+, CH+. Those molecules can form there. And then we have the neutral molecular layer, and if it gets even colder, things will start to freeze out in the form of ices. And a lot of that can be found in a whole sequence of reviews about what the chemistry is in these planet-forming disks. Now, interestingly enough, we know in the interstellar medium more than 200 molecules easily have been detected. This is not the case for planet-forming disks. So I did an update of this table just yesterday, And I think up to now, this is probably what has been detected. So up to 6 atoms. The color here gives you actually at which wavelengths the detection was made. All the black stuff comes from radio telescopes. These are the 2 editions from ALMA. This is the latest one from this year. So I only put the references for the most latest molecules. H2S, I think, is the latest one from 2018. So it does not mean, you should not go off and think now that these disks are less complex in their molecular content than the interstellar medium. It only tells you that if we look with the same telescopes that we use to study molecular clouds at these disks, the disks are tiny compared to a molecular cloud. A molecular cloud has thousands of parsec in size sometimes. These disks are like 100 astronomical units. So 1 parsec is about a few 100,000 astronomical units. So you see these disks are tiny, tiny compared to molecular clouds. And so the surface area with which they emit is super small. We need telescopes like ALMA in order to drive this further and to see more complex molecules. And we are not there yet. So, okay. What happens in a planet-forming disk? I like to do this one. What happens in a planet-forming disk if the temperature drops below 150 Kelvin? The water molecules stay in the gas phase, so we have supersaturated water? Or do the water molecules become very immobile and locally cluster together to form ices? Or do the water molecules absorb on the surfaces of small dust grains and form ices? Can I get some hands? So who says A? B? C? Ah, great. Okay, yes, obviously it's C. The dust acts as a condensation seed. And we come back to that because there are different types of models out there, and some models actually form rather this approach, which we think is not appropriate to use in the case of disks. Do we see that? Yes, we actually observe it. This is a very nice example. It's a disk around a young solar type analog, maybe TW Hydra. This is the continuum emission. The nice thing is we look at that disk face on. That's why you see no projection effects. This is the CO emission. And this is a very nice molecule, N2H+. Probably not many people that used it before, especially in chemistry. It's not that much useful. For us, it's extremely useful because N2H+ actually sits everywhere where CO is frozen out on dust grains. So the extent of that N2H+ ring here tells us about where the snow line, the ice line is for CO to freeze out on dust grains. If CO is in the gas phase, it actually destroys N2H+. So they cannot live together. So we can use these molecules as a tracer of where these different transitions occur in the disk. Similarly, there are attempts to use molecules in order to figure out where the water snow line is. So these molecules, besides studying just the complexity, I mean, how big of molecules can you get in disks, also helps us to understand about the structure of the disk. And you can ask yourself, like, well, is there a lot of agreement between observations and models and what we know from Earth, from our laboratory? And I want to show briefly 2 examples where directly from the observations, from the CO emission that we see as a function of radius. The CO emission is a direct measurement of at which temperature that CO molecule is rotating in the disk. We can measure that temperature and we see a nice plateau here. And this plateau comes about because it traces the surface snow line of CO. The CO freezes out below a temperature of 21 Kelvin. This is consistent with laboratory measurements and theory and even the densities that we think these disks have. So we see the plateau at 21 K. These are 2 different objects that this has been shown. So it traces actually the surface snow line where the 21 Kelvin contour is reached. Underneath that, the CO is freezing out on the dust grains. Above it, it's staying in the gas phase. So this is actually a very nice work, and there is very little we can know about the detailed chemical composition in the regions where the planets are actually forming 1 to 10 astronomical units, we cannot directly observe it. Very, very hard, because the disks are optically thick. But now you can use all the models you have at hand in order to use your observations and extrapolate to what that model may look like at the midplane. And this is what we try to do. So there are several groups, and I'm just leaving this up for people who are interested to look up some references. We can actually model what the ice to rock mass ratio, water ice to rock mass ratio is in these disks. And it is not the same whether we assume that the ice is freezing out on dust grain surfaces or if we just use thermodynamic equilibrium. We can also trace the carbon over oxygen ratio and see if it has any relation with, say, the composition or the atmospheres of planets that are forming. And we can also trace in these models the detailed composition of the ices as a function of distance from the star to make a link to the cometary composition, for example. So all of this is interesting to see to which extent actually planets and minor bodies do inherit anything from the chemical composition of these disks. And the jury is still out. And I'm going to skip this part and come to my conclusion. So I think what I wanted to convey is actually that these planet-forming disks do have a very distinct shape. They are geometrically very thin, but flaring disk structures with typical sizes up to a few hundred astronomical units, which is in fact at that stage much larger than what our solar system is now. So where is the mass? Observations of dust and gas in planet-forming disks from the near-infrared to sub-millimeter wavelengths, they provide a picture of the structure and also the composition of material. But inside 10 astronomical units, it's very difficult to directly access what the composition of material is that goes into the planets. We can use detailed disk models to describe the physics and chemistry to help fill that gap and actually infer the composition in the inner disk. And interestingly enough, with the new observations, especially with ALMA, we witness now the first processes that we attribute to planet formation in these disks, and we see direct evidence of that. Maybe even embedded protoplanets. So these disks are extremely complex in their composition. It's very hard to understand a lot of these aspects. The crystallinity of dust and ice and also the molecular complexity can be used to study the similarity to minor bodies in our own solar system, the stuff we are actually made of. And this is what Nada will actually talk more about in his next lecture. Thank you.